All right, I'll try and keep this as uncomplicated as possible, but to understand lattice energy, you need to understand that the first thing we're talking about is um, an ionic bond. So just real quick, this is from one of my AP slides. So we have energetics of ionic bonding, which is where lattice energy will come in. So as we saw, we have ionization energy. That's what this is right here, I1. It requires 495 joules of energy to remove an electron from sodium. But in chlorine, its electron affinity is negative 349, so it gives that much energy back. All right, so then we have the Na, which gives its electron to the chlorine, which that was positive, this is minus. The electron is hanging out with chlorine and it's happy. And then this plus and this minus will attract to each other to form the covalent bond of NaCl. It is the measurement pretty much of the attractive forces between this plus and this minus that is what we call lattice energy. Okay, so these numbers don't explain why the reaction of sodium metal and chlorine gas to form sodium chloride is exothermic. All right, so this structure right here, this cube, this is what we're going to call a lattice. I can't remember if there's two T's or not, but whatever, that's what we're going to call it. And that is where the sodium, which is purple, and the chlorine, they form this organized structure. And that's the word for that is a lattice. Okay, so the third piece of this puzzle is what we call lattice energy. And it's the electrostatic attraction between the newly formed sodium cation and chloride anion. So basically these things are vibrating back and forth. All right, the electrons are transferred and then they move towards each other, kind of like two cars moving towards each other, and then they stick together. And since they're no longer free to move and shaking around, they give out some energy, and we call that the lattice energy. Okay, so here we go. The third piece of the puzzle is the lattice energy, the energy required to completely separate a mole of solid ionic compounds into its gaseous ions. The energy associated with electrostatic interactions is governed by Coulomb's law. And Coulomb's law says that the force of attraction is equal to the electrostatic constant, which is K, which we don't care about in this one. And it's multiplied by Q1 and Q2 over the distance squared. And this is usually measured in radius, so it might be r squared. Okay, Q1, that's the charge of one thing we're talking about. So like the sodium cation. Q2 is the other thing. That would be the chlorine anion. So Q1 and Q2 are the two charges. And then D, that's how far away they are from each other. This is Coulomb's law, and it governs every electrostatic attraction that we have. So what your teacher is asking you on how to line up from increasing to decreasing order of of lattice energies can be answered with Coulomb's law, or with these two summaries. Lattice energy then increases with the charge on the ions. It also increases with decreasing size of the ions. So coming back to Coulomb's law, what it's saying is if Q gets bigger, lattice energy gets bigger. Okay, so if Q gets larger, either one of them, then the lattice energy, which is basically this force. Or if this number, the distance, if it gets smaller, this also makes it larger. So we can apply that pretty simply to the question she sent, which I don't have here, but I'll look for it. All right, so I did something dumb here and I cut off this part. It said which set of compounds is arranged by increasing magnitude. So we're looking for the one where it's small, on the left and big on the right. So let's just plug in some numbers real quick. According to Coulomb's law, we just take the charge of each ion. So this is +1 times -1. So the top here so far is -1. All right. Cesium is also in family 1. Iodine's also in family 7. So it is, also a -1. Magnesium here is a +2. Sulfur is a -2. We multiply those and we get a -4. All right, so we have 1, 1, and -4. That's a good sign. Let's look at the rest, though. All right, we have -1, we have +4, we have -1. So this one is gone. Because 4, we always need magnesium sulfide on the right. So it's either this one or this one. We can see already here this one's going to be wrong. Because magnesium sulfide is a 4. Okay, now the next question is, how do I know between these two? So first off, we had the Q1 times Q2, and that eliminated it, so we knew the magnesiums. But if they tie, then we need to worry about the distance between them. All right, so to get this number, the distance to be as small as possible, we want the smallest atoms. All right, so chlorine and sodium are towards the top of the periodic table. All right, chlorine's here, NA's over here. That's ugly, but whatever. So since these are close, they're both pretty small. But cesium and iodine are both down here. All right, so this one's a big one. These are the small ones. So if we're talking about needing this to be a small value, then we're looking for the smallest atoms. And so the lattice energy for NaCl is larger than this one. So we're going to need cesium iodide, and then sodium chloride, and then magnesium sulfide. Okay, hopefully that helped, but we'll